Hello there.
With
Okay, Android, is Lewis Capaldi the most successful music artist of all time?
No.
Is Lewis Capaldi the most successful artist of all time with long, flowy hair?
Still not quite.
With flowy hair, who was born in Glasgow and whose middle name is Mark.
Based on the criteria provided, Lewis Capaldi is the most successful singer of all time.
Got there eventually.
On January 2nd, over 300 people were seriously ill with flu in our local hospitals. That's the equivalent of 10 full wards. So this winter, our best chance of staying well is by getting a quick...
Good evening and welcome everybody. This is Obi-Wan Piz for and Simplex Pachinko. We're going to be doing some math tonight. So, I was just looking for a particular proof of... Oh, don't do that. What? Oh no. I was just looking at, trying to figure out if I had a fundamental theorem of calculus in here, because I had a particular method of introduction that I wanted to go for, but I don't think I do. Unless... Now that's related rates. Yeah. Boo. Alright, let me try again then. Let's move to Calc 2. See if that's somewhere near the beginning. Seems like no. Yep. That's too bad. Let's go with search here. Really? That is definitely unfortunate. Fundamental theorem of calculus appears to not exist in this particular context here. Oof. Okay. April of one of these years. Indefinite integrals. Sounds promising. Newton's method. L'Hopital's rule. Riemann sums. Here we go. May. Okay, there's the fundamental theorem. Yeah, this is from 2017, so this is kind of before I really... That is really too bad. Well, curses. I had a good lead-up that I had in 2022 to 2023. Wherein I went through and like actually got the reason that the fundamental theorem of calculus worked. Yeah, that's too bad. I'm okay, I promise. Okay. Sorry for the delay. Anyway, we're doing alright. How's everybody else doing tonight? This month's next book for our book club that we have here amongst the Americans generally and a few Brits is an Ursula K. Le Guin book called Lathe of Heaven, I think it is. Yep, The Lathe of Heaven. And the synopsis was basically some guy starts thinking about stuff and then it creates it in the real world. And so this direct manifest of stuff that happens in this guy's head versus stuff that happens in the real world ends up becoming like an important plot point in the book. And he goes and sees a therapist who decides that he's going to take over the power of, like, he's going to basically implant ideas into this guy's head, I think, is how it's going to work. And then that kind of shapes the world in the way that he wants it to. So, should be an interesting one. I had also picked up, like, the week before, The Dispossessed by Ursula K. Le Guin, and haven't really actually gotten started, but it's going to take another week or so for our book to come in, so whatever, I've got time. Something. Okay, so for tonight, we're looking at the fundamental theorem of calculus. Oh yeah, and it's also bonfire night, so people are launching fireworks all over the place. Alright, so the way we had been doing this was we were talking about the Riemann sums. into integration. And the way that worked was we were saying that we wanted to take the sum of the areas. It's probably a terrible idea. Alright, so... No, I don't want to go to 16. Jeez. I'm going to go to 4. That one's going to be at 16. There we go. Okay, so the way that we're doing this is we've got y equals 16 minus x squared.
What do you see? Great ideas. Start.
And we said that we wanted to break up the area under this curve into some number of rectangles. Ew. But hey, this technically works. So in order to figure out the area of each of these individual rectangles, what we need to do is multiply its width by its height. So the height is going to be the same as the function, and we'll rename y. Instead we'll put f of x. Makes it a little bit easier. So this is f of x sub I multiplied by the width of each one, which is going to be delta x. And we can make it delta x sub I in order to say that each one of these can be completely different sizes, as evidenced by what's actually in the picture. Oops. Most of the time we don't bother with that, and we just say that delta x is going to be one particular value in the street. How thick do you have to be? Right, so the area of each individual one is going to be the function value. And we're just subscripting with i's, and then multiply by the width of each of the rectangles, or the distance between each of the x values that we have marked. So overall, right, we're going to get a rectangular area, width times height. Simple enough. So the Riemann sum is where we start to generalize this, where we're saying, okay, we're going to take f of x sub I multiplied by delta x sub I. And then what we're going to do is say I is going to go from 1 to n, however many of these things we're going to use all the way across. Good evening and welcome everybody from Zach's channel, e to the 2i pi. Poison mouse. Oh no, what have you walked into? Scary stuff, yes, definitely. You're doing calculus stuff. Alright. Well, let me know if you have any questions, and we can drop what I'm doing immediately. Okay. right? And then when we take this and we say, okay, now we're going to take the limit as n starts going to infinity, we're going to have an infinite number of vertical slices through this particular curve, and therefore we're going to have a whole bunch of like wafer thin salami or whatever other giant meat they've stuck onto the thing at the deli. I'm not hungry, I promise. Alright, this is going to end up being the integral as we go from some particular a to b, which, again, a was going to be our, like, x. Well, okay. I don't want to break conventional notation here, but we're going from, like, x1 is going to be a, and then x sub n, x sub n plus 1 is going to be b. With the way I've done it, that's how it's going to be. Alternatively, we could go from 0 to n instead, but that works too. I believe that is what we have suggested. Monday the 17th, 8 p.m. my time. Yeah, that should be okay. I need to re-verify with my family, but I don't think there's anything going on. It's going to be a Monday night. And obviously, you need to go and do what you need to do at the moment, so... Yep. We'll catch you next time. And thanks for bringing everybody over. And hi to everybody else that I didn't actually introduce myself when you came in. Sorry about that. My name is Obi-Wan Pez. This is N-Simplex Pachinko. We did only, like, sort of just start a little bit before you all got in. So I just wasn't thinking about it. Woo, clickbait. Yeah, so, right. On this channel, we do mathy stuff twice a week, and we do gamey stuff currently 3 times a week. Sundays we have our base building game, which currently is Satisfactory. Tuesday we have our kind of miscellaneous game, which at the moment is 9 Souls, which is a comfy little cozy Tai Chi kitty game. Trust me. And then Fridays we have For the Long Game. So we're currently working on Against the Storm, and soon after Against the Storm is done, we'll figure out what else to do. I do know that we have Final Fantasy VII Rebirth still to play in the queue. I need to go back to Remake and like finish out a couple of the hard mode quests and things like that, but you're going to play Sleep in a bit? Yep, nice. And in that case, right, find the series of Taylor around p equals 0, radius, and the radius of convergence 4, e to the z over 2 plus z squared. Now, I think that's going to be a complex analysis question, eh?
On January 2nd, Over 300 people were seriously ill with flu in our local hospitals. That's the equivalent of 10 full wards. So this winter, our best chance of staying well is by getting a quick, simple and free for many people flu vaccination, especially if you're older, pregnant or have a long-term health condition. Children can be super spreaders, so get them vaccinated too. Check your eligibility and find your nearest vaccination centre at letsgetvaccinated.co.uk.
Okay. So the radius of convergence on this, we can figure out in much the same way we did with stuff from Calc 2, where we could start by looking at what kind of behaviors we can see. So in here we have this e to the z, which belongs up top. So this goes to infinity exponentially. Right, as x also goes to infinity. And 2 plus z squared is going to go to we've got some options here. So either the denominator can go to 0, or the denominator can go to infinity, as like our two major problems that could potentially arise. This is only going to happen if z squared is equal to -2. Therefore, this is when, right, we have singularity points at absolute value of z is equal to square root of -2. And technically, I probably shouldn't put these absolute values there. Right, yes. Right, reason being that technically the absolute value of that would just be the square root of 2, but that would just confuse everything. So here we're looking at, right, plus or minus I root 2. Right. So total definite singularity points at those two locations. No excuse. Serious problems. All right, so if z squared is going to cause this to go to infinity, we also know that this is going to be a square function. You know, quadratic. So we can notice that e to the z is going to be much greater than z squared for, certainly for real numbers. And for the imaginaries, I would imagine that something similar is going to happen. So the top is going to be much more strongly involved, right? It's going to go to infinity faster than the denominator will. This is one of the weaknesses of not thinking about this fully two-dimensionally in terms of the complex numbers, because as we start getting imaginary numbers into z, then we start getting negative values, but the numerator is still going to be much larger. So I don't think we need the caveat. This is just saying that this is, you know, of a larger order of growth. Right. So whatever it's doing, it's going to go off to whatever infinity it's pointing to faster. So I guess I could just say, like, you know, it's that. The size of e to the z, regardless of whether e to the z is actually positive or negative or imaginary or complex or whatever. So that number is going to be just much larger. So overall, as our z goes off to infinity, the fraction f of z is also going to go off toward infinity faster. Or at the very least, e to the z will be the fundamental thing that takes care of it. And then you just have to look at what z squared is. Is it positive or is it negative? Is it going to keep the same sign? Is it going to flip the sign? So you just kind of have to know what is going on there. I don't offhand. I could probably calculate it, but it might take a while. Okay. If we're going to do this as a Taylor series, then what we can do is turn this into a product of Taylor series, which is going to be terribly inconvenient, but can work. E to the z, I think that's the sum. Just 1 plus x squared plus x cubed. Blindly. Oh, that is interesting. What's the radius of convergence? So, for what values of z are we going to get finite limits? Oh, right, yes, over... Man. Over the factorial term. Completely forgot about that. Alright, 1 plus x plus x squared over 2 factorial plus x cubed over 3 factorial plus etc. Okay, and then something like that. 1 over 1 plus x squared is probably going to be the way that that works. Yeah, I guess. If I'm gonna stick with a particular variable. Okay, 1 over 1 minus x is going to be 1 over 1 minus a plus x minus a over 1 minus a squared. Yep. Plus x minus a squared over 1 minus a cubed, etc. So, if we want, 1 over 1 plus x, again, z, yes, but we'll get there. One half sum n to infinity 1 over 1 minus negative, yeah. Oh, right. I want a squared as well. Yeah, no, that's fine. Instead of x, that a is the location, right? Yeah. Well, okay, so in our language above, it's p. So that's just getting rid of this stuff. Nope. Is it that simple? Yeah. So just z to the n.
Sometimes creating an ad campaign can feel like you're talking on mute.
Sorry, we can't hear you. Say that again?
But advertising on Spotify can help your business turn up the volume. With our easy-to-use ads manager, you can create new audio ads from scratch or repurpose existing video assets. Then we'll deliver your ad to an engaged audience that is ready to hear and see your message. It's that simple. Learn how Spotify can add more to your mix at ads.spotify.com.
Right. So right, if this was over 2, then we can multiply it across and end up with the 2 that we had up top there. But then we'd get an extra 2 on the top. So here we'd have to have another half at the bottom on the outside. Wait a minute, no. No, I'm wrong. Because in order to balance... No, actually that's good. Okay. In order to balance this, every term with an x would then need to be just divided by 2. Oh, inside the power. Okay. So I'm not getting the first term to change at all. That's another interesting bit. Oh, because I didn't do it yet. Jeez. Right, you multiply both top and bottom by 2 in order to make this work. Jeez. I was also wondering where you got the extra 2's from. It's from this, right? The 2 at the top has to then be divided over. So this is going to be 2 over 2 plus x squared is equal to that. Same thing. So 1 plus negative x squared over 2. Okay. We can fix it, I suppose. Minus that plus x to the 4th over 4. So yeah, it's at least nice in that regard. Minus x to the 6th over 6. Nope. To the 8th. Plus, and then continue from there. Then we need to divide both sides by 2. Then we're going to end up with 1 over 2 plus x squared is equal to 1/2 minus x squared over 4 plus x to the 4th over 8 minus x to the 6th over 16 plus, and then continue like that. Yep. Okay. And then yes, you want z, not x. So we can take that back up to here. And we end up with 1/2 minus z squared over 4 plus z to the 4th over 8 minus z to the 6th over 16 plus dot dot dot. Okay. So we have the Taylor series. It's now a product of 2 infinite series. So one is that you could try to multiply this all out pointwise. But that seems not nice. We can't just multiply the general terms together and be like, okay, well, if I multiply, you know, this is going to be z over, or z to the n over n factorial, and this is going to be 1/2 alternating sign z to the 2n, 2k, I guess, over 2 to the k. Not quite. Something like that. You would not be able to multiply those two things together and just be like, oh, there you go, you get this thing. Because this is a two-dimensional multiplication. So we need something that ends up with n squared terms. K squared. However, it is true that when small, these terms will multiply very quickly to get toward 0. I have my cards open. Taylor series. Differentiating, integrating, right? Not really. Ah, there you go. Okay. It's been a while. So the recommended method of doing this is going to be find we essentially do a limit comparison. It's not even a limit comparison. This is the it's a comparison test. If we use the limit, no, if we use the comparison test here, oh, right, I guess it is a limit. Right, as n goes to infinity. Thank you, ratio test. We can find out where it is specifically, like what the... Oh, did you get it wrong?
So this winter, our best chance of staying well is by getting a quick, simple and free for many people flu vaccination, especially if you're older, pregnant or have a long-term health condition. Children can be super spreaders, so get them vaccinated too. Check your eligibility and find your nearest vaccination centre at letsgetvaccinated.co.uk.
At QuickFit, we know winter's nearly here. Everything becomes pumpkin spice flavour, and you're scraping ice off your windscreen with your credit card. And while it's getting colder, it's a good time to check your tyres. At QuickFit, we stock Bridgestone to...
I guess the problem here is this is not a... Oh, yeah, it is. Never mind. Jeez.
So while you get winter ready, make sure your car is too. Book today at QuickFit.
I was like, well, it's not a discrete function. Yes, it is. We're using the Taylor series for it. Now maybe I'm looking at this in terms of just trying it with f of z without the Taylor representation of saying like, well, what's this going to do for you know, a continuous function. So if we were to say what would happen if we did like e to the z plus 1 over 2 plus z plus 1 squared over e to the z over 2 plus z squared. I don't know that this would actually work, because here now we're talking about continuous versus discrete and all sorts of other stuff. But this would end up being e over no. What's going on? 2 plus z squared here, and 2 plus z plus 1 parentheses squared here. Essentially, this is going to turn into just e. As our limit z goes to infinity. Let's try and prove it. Can go a bit further. This is going to be z squared. It's going to be 2z. And this is going to be 3 overall. Hang on. That's not the same. It's not z going to infinity. That's my problem. Ah. It's the number of terms that are going off to infinity, not z itself. Z is completely independent of the variable that we're using. So, what we want is a value for z that's going to cause, going to cause a singular point. Or an asymptote. Right, it's not z. It's not of n and n plus 1. It's of z, but this Taylor is going to be of a size one larger. So we're taking it, I mean, we're sort of shifting it. Yeah, Poison, I may be just misinterpreting it.
Story you love, every invention that moves you, every idea you wished was yours, all began as nothing. Just a blank page, asking a simple question. What do you see? Great ideas start on Mac. Find out more at apple.com/UK/.
Right, so the issue is...
Leap. It's about being free at heart. It's about letting go. No matter the landscape or the experience. No constraints, no limits, just me. Leap, the original eau de parfum and vanille.
Right, I don't think we're allowed to use that. So... Yeah, you can also try asking Penn. I know he was on. Well, I thought I saw him on. Alright, well, have a good night. Sorry about that. Oh, hey, Zach. Hey, Zach. What would you suggest for trying to figure out if this f at z around the origin or no, trying to find the radius of convergence of that particular complex function. Now, I had said part of it was find the Taylor series for them. So I split it up into the two things, numerator, denominator, which get us to two series, which obviously can't be multiplied very nicely. But where would we go with trying to find radius of convergence of two complex valued functions? The product of two complex valued series. I had gone and started saying, oh, let's try to do a ratio test or something like that, where the ratio of these things is less than 1. But I started conflating the n with the x, or the z in this case. So obviously that doesn't work. e to the z is convergent everywhere. I'm not sure that I necessarily understand why. Just because... Is it because... No. Never mind. I was going to say, oh, it's my harmonic or something, but no, that doesn't work. I'm thinking of real values, I guess, that are greater than 1. Right? So real values of greater than 1 are going to cause e to the z to be not a convergent function, unless I'm thinking about this wrong, which I probably am. On the ratio theorem on e to the z series. Is it the harmonic? Yeah, because it's one of these. Okay. Okay. So the n value is going off to infinity. Z could literally be anything, and as long as z is a finite number, then it's going to... Yeah, okay. Fair. Okay. So, ads are about to start. We'll come back to that. So, thank you so much, everybody, for coming, and we'll be back in 3 minutes once I go stand up and stretch.
To get better rates on mortgages, loans, and credit cards, you don't need to know the friend of a friend of the second cousin of a dog walker who went to school with the adopted son of a reflexologist who's currently plant sitting for the stepsister of a social media influencer that lives next door to some guy who works in finance. You just need a little help from Experian to improve your credit score. Download the Experian app and check your credit score and report for free today.
Hello and welcome. This is the Michelle Hussein Show. I'm Michelle Hussein. I speak with people like Elon Musk.
I think I've done enough.
And Shonda Rhimes.
That's so cute.
This will be a place where every weekend you can count on one essential conversation to help make sense of the world. So please join me, listen and subscribe to the Michelle Hussein Show from Bloomberg Weekend, wherever you get your podcasts.
You certainly ask interesting questions.
Be quiet. I hear the thunder that comes from far away. It's like a noise in my head. Oh, these were hearts. These were hearts. It gets you deep and leaves a scar. Oh, these were hearts. These were hearts. It gets you deep and leaves a scar. Curtains fall apart and it frees your heart. It's no longer the same. Curtains fall apart and it frees your heart. It's no longer the same. We need to get up. We need to get out of here. We need to get out of here. All we need to do is to get out of here. We need to get out of here. We need to get out of here. All we need to do is to get out of here. Curtains fall apart and it frees your heart. It's no longer the same. We need to get up.
Alrighty. So, I think we'll be doing some, sure, let's go with some of our Tangsudo karate. So tonight, what shall we do? Probably try and Pin on 5 again, which is a bit older. Haven't done it in a while. Just do a bit of a warm-up. Rock back and forth. Balls of the feet. And more or less just let the hands go where they're going to go. Don't rock too hard. Find a nice steady rhythm. And same here. Kind of let them fly downward a little bit and then put a rock in it and keep the energy moving. Last night when we were doing Tai Chi, I also forgot we didn't do the bear part. But it's alright. Alright, so for Tang Sudo. We have the basic forms of the Taego series, which more or less work on an eye shape. So oftentimes what we do is with Taego 1, 2, and 3, 1, 2, and 3, the basic idea is that we're doing some sort of block immediately to the left after we do our bow in stuff and all that good stuff. Go to Junbi, which is the ready position, and I'll make this bigger so you can actually see it. Anybody who's interested. Alright, gotta pick this up tomorrow. So more or less the way that this works is that we start from Junbi, and then we do some sort of block to our left, followed by a step and some sort of attack. And then we go the other way, a block and an attack. And then a block to the front, and then an attack 3 times to the front. We make a left-hand turn 270 degrees, and then an attack, and a block back this way, and an attack, and then a block to the center. 3 attacks again, a block 270 degrees to the left, an attack, and a block, and an attack, and return to Junbi. So that basic setup is involved in a lot of the Tangsudo forms, which includes all 3 of the basic Taegos, the Pinon series 1 through 4. 5 we start breaking it. More or less we're still doing the same thing, it's just that it starts getting away from the standard eye pattern, where we end up starting this way. So we do an inside out block here, but then instead of stepping forward, we end up doing going to a Chongkul stance without moving our front foot. So we had been here, and now we just straighten up and make all this like straighten the body out, and now we're in Chongkul stance. And then we come here, do a tension, which is as if you're like grabbing somebody's hand and wrenching it off of you, or a number of other things. It could also just be helping you breathe, because oftentimes when you do these forms, you get tired very quickly, right? So we go to come on, Fugel stance, which is a defensive, backward weighted stance this way. And then again, we straighten everything out and go back to Chongkul without moving the front foot. Alright, and then start here, go back over here. Then we do a twin fist. So our top fist is hiding our bottom fist. Usually the top one's going up toward the chin area. The bottom one is going to the solar plexus. So if you go like this, you kind of hide the fact that you're also punching at the solar plexus here. Okay, so we go here. Step, cross block down, cross block up. I got my notes over there somewhere, I'm sure. See if I can just do this muscle memory wise. So we had it been over here. So we do a down or cross block down, followed by a cross block up. This is like if somebody's coming down with a weapon or like a knife or something like that, you come up and block it in here. Now I don't remember what I'm doing with this hand. I could also be on the complete wrong foot, because that's happened before. So if we come this way... Alright, let's... That's wrong too. Okay. Twin fist. Cross down, cross up. Right hand grabs, left hand loads to hip. Right hand pulls in while left hand punches. Okay, so we were correct, and then it starts here, goes to a twin fist. And then as we start up, we're going to do a down block, up block with more like choppy hands. Right hand grabs whatever's up here. Left loads. And then we're... Nope, that way. Ah. That way. So we're taking whatever's up here and we're pulling it down to our hip. And at the same time, we're punching up with the left. So this goes down, up, grab, load, switch. Okay. Then from there. Yeah, cool. Hang on. Wait a second. Wait a second. Right jungled. Oh, interesting. Yeah. Right to left here. Here. Right to left. Yeah, right jungle, left. Oh. Yeah, okay. I guess now I'm on the right foot, though. That's good. Okay. And then right Kima throat punch. Okay. Then we go from here, back switch the other way. Then this one. Right Kima throat punch. Ah. Then here, we go back to this side, and this is where we do that one move that I'm so fond of, where we end up doing crescent kick and then face smash. Okay. Yep, okay. So we've come back over here, done a throat punch there. We load to the hip, we do a chop out here, to like throat, whatever you can manage. And then that's when we do the smash here. And then we load back and do a double punch, which is like ends up this way. But basically we're coming in to somebody here, and then we come back a little bit and do a second hit as we're stepping away, because now we've seen an opponent behind us that has something that's going to try and sweep our leg out. So from here, we do a quick little hop over whatever it is, turn around, do a cross block to block it, and then, is it twin fist here? Yes. Right, so here, when we do this, we're also cross-legging, or we're also cross-blocking potentially a leg that's coming in for a kick, which means that if you can grab the fabric behind their knee with one hand, grab their foot with the other, and twist them around, which could be a lot of fun. For some definition of fun. Okay, then here... What? Left hand around left hip. Oh yeah, pierce, rip, and then we take a step and do the same on this side. And then that's going to be the end of that one. So we're here, we do a D to draw, just like that. Step back, yeah. Okay, cool. So this one, Pin on 5 ends up being much more back and forth rather than using the eye shape that we had been doing for all the rest of the forms before. That is for blue belt. So when someone's going for blue belt, or no. Yeah, okay. When somebody's going for second degree brown belt, then they're doing Pin on 5 and Keep on 4. So those are the two forms that we have that typically blue belts will learn for second degree brown. Right, Keep on 4 is a little bit harder to do, but let's see how much I can actually remember this. Alright, go here. And that might just be my black belt. Right. Now hang on a sec. This is my handwriting. But I swear I don't recognize this. Left foot Kima. Hands in front. Here? Alright. Hands to block up. That's weird. Whew. Okay. So we went here. We come this way. Right, okay. Now I get it. So we spin. Not spin, but turn. 1, 2, 1. Elbow smash. Pop, pop. And then this comes back down here. Down here. And once we're at this point, I'm going to turn around because it's really boring if you're just looking at my rear. Right, so we end up coming down with a double block, but essentially this can also be used as a weapon to hit something out of the way rather aggressively. Okay, so then from here, we do... It's an up block and up... It's a punch, then an up block, which is different than normal. So here... I don't like that. If we were here... Yeah, that's it. So essentially what we're doing is we're coming in like this, striking at something, giving a punch like directly from this area where we're already here. So we pop out like this, and then we see that somebody is also attacking us at the same time, so we go into an up block in a more defensive stance. This is also going to bend the knee, which causes us to end up with power when we come back up and strike, but then, oh no, somebody else is attacking us, so we have to go into a defensive stance this way. It's not pretty. And it's I'm probably exaggerating it, so you know. So here, 1, 2, 1, 2, and then we do Fugusido.
So while you get winter ready, make sure your car is too. Book today at quickfit.com or your local centre. Quickfit. Drive away happy every time.
It's not RGHV, it's Bronco.
What? Right, pierce left, right, step left. It's a crescent kick first, then head smash, then the two things. But either way. Right, left, right, okay. Take those. Right, reverse punch up block, left punch up block. Okay, so it is right first. Okay. So we come here, we're doing that. We do go right block this way, left block this way, and then we come through and do a cat stance with a strike like this, and then we should move into Fugusido. I mean, technically I'm on the correct side of the room, so that could work. Fugusido, left, right, middle, and then go back to tension. Yep. Okay, let's try that all once. Boy, this is not particularly easy. Let's try that again. So step, do this one. Left, right, left. Then we do a crescent kick. Step into Kima. Head smash up, down. 1, 2, 3. And oh, that's why I'm on the wrong side. Or I was on the wrong side. So here we do right, left. Ah, that's what it is. From here, we end up doing an up block with a thrown thrown chop, and then that's where this wrap comes in. Makes much more sense now. All right, I think we'll call that one good. You guys get to watch an old man learn something. Alright, thanks for sticking around. How we doing? Okay. Okay, so then the other one, right, is going to be n goes to infinity of the following. This is, so we have to know what this is first. This was 1/2 times the quantity of 1 minus z squared over 2 plus z to the 4th over 4 minus z to the 6th over 8 plus, right, z to the 8th over 16 minus ... Okay, so both of these are going to have a 1/2, and both of these are going to have a -1 raised to the, this is going to be n plus 1, and this is going to be n, or potentially n plus 2 and n plus 1, or something like that. But either way, they're going to divide out. So we're going to get a negative on the inside, and it's inside of an absolute value sign. So the negative part is just going to be ignored. And then we have that. So if that's the 0th term, right, that's going to be z to the 0 over 0 factorial. Wait. Which then makes this z squared over 2 factorial. Oh, no, it's not factorial. It's 2 raised to the n, whichever I we're on. So 0, 1, 2, 3, 4 is going to be the powers on those. So this is going to be a -1 to the, let's just do k so it's not so confusing, over 2 to the k half on the outside, or we can add the +1 to the denominator in here, but I don't like doing that. Right, and z to the 2k. So this is going to be z to the 2 parentheses k plus 1 over 2 to the k plus 1 n. I'm doing n, stick with n. 2 to the n plus 1. Then over here we're going to have z to the 2n over 2 to the n. All this stuff again goes away. We just get a -1. We're going to get a z squared on top. And on bottom, we end up with a 2. So this appears to be convergent everywhere because there is no n. Right, so Poison Mouse. I'm pretty sure you're asleep by now, but maybe you're watching the VOD. That should be your answer. There is, like, it should be convergent everywhere. Wait, hang on. Nope. It's convergent when z squared converges. But anyway, the other fact that we know is that the limit as n goes to infinity of f of n times g of n, where limit n goes to infinity of f of n is going to be this capital F, and the limit as n goes to infinity of g of n is going to be capital G. If all of this is true, then limit as n goes to infinity of f of n times g of n is going to be fg. Capitals. Because we can spread out the limit as n goes to infinity into as many different places as we want. It's not a linear operator even. Well, no, it is. But it's even more than like any particular linear operator. It spreads through everything. And if you have something that doesn't have an n in it, it just passes out as a constant. And here we have propagation, I guess, would be a better word for it. So like limits propagate to literally everything. You could give them individually to every little thing in the entire equation that you have, expression, whatever you've got. Or you can leave them where you have larger structures. Doesn't much matter. It does all the same stuff as long as everything is evaluated eventually. Yeah, I guess this means it's just literally everywhere. i.e. z is not equal to infinity, or absolute value of z, right? Z cannot be infinity itself, but if it's literally anything, we're fine. Okay, this means that the limit as n goes to infinity of absolute value z squared over 2 can be multiplied by the absolute value of z over n plus 1. And so this is going to be same as absolute value of z to the third over 2 parentheses n plus 1. It's going to mean that this is conversion everywhere. Again, the absolute value of z can't be infinity itself, but like we've established that z is a complex number, so infinity is not a complex number. That's actually a good point, right? Is that? Yeah, it's convergent because any particular z value is going to get you a single number. I think that's the answer. Should be convergent everywhere because as n goes to infinity, that whole value goes to 0. Oh, wait a minute. Ratio must... That's not conversion everywhere. That absolute value z squared over 2 is less than 1. Okay. So this gets us the absolute value of z squared must be less than 1/2. And so that is a circle. Right here, r equals 1/2 is the circle itself, and this is for z squared. So if we want this for z, then we have to take the square root of that, which means that our circle is actually going to get bigger, and we're going to be at 1 over square root of 2, negative 1 over square root of 2, 1 over square root of 2, or rather I over square root of 2, and negative I over square root of 2, or what are at these 4 corners of the circle. Lol. Right, and then all of this stuff is going to work. Anything inside of this circle, not including the edge itself, this is true but not helpful, because the other one was convergent literally everywhere. Alright, so it's equivalent to Z is less than absolute value of Z is less than 1 over square root of 2. So the radius of convergence is 1 over square root of 2. Okay. There we go. Alright, Poison Mouse. We got it. Okay. We have been talking about the fundamental theorem of calculus. In here, we'd said back with the Riemann sums, if we let n go to infinity... Ooh, Aurora likely tonight.
Sean has had some good ideas over the years, but using Canva was a really good one.
Okay, we get f of x dx.
They looked good. Really, really good. Next thing he knows,
And
bought the lot, including the car. Now Sean doesn't know how he's gonna...
the fundamental theorem of calculus has kind of two prongs that go with it.
Every story you love, every invention that moves you, every idea you wished was yours, all began as nothing. Just a blank page, asking a simple question. What do you see? Great ideas start on Mac. Find out more at apple.com/UK/Mac.
Alright, so the fundamental theorem of calculus is going to start using a similar setup for this. And so what we're going to do is we're going to say, well, if we look at what the picture represents for this, and in fact if we extend this in the opposite direction as well, because it's perfectly possible. Almost. Close enough. No. -4 and 4. Right, these are going to keep continuing. However, what we're only going to be concerned with is what's going on, really, between our starting point and our ending point, wherever A and B are on this thing. In order to make it easy, we'll let A be equal to 0. And our B could be equal to 4. So what we want is what's going to happen to our area under the curve as we're moving from a equals 0 to b equals 4. Again, here this is kind of like our salami cutter at the deli, right? We're taking these super thin strips. In fact, the strips we're taking in mathematics are so infinitesimally small that it would take an infinite number of them to get literally anywhere. But once you stack them all up, you can find that they do, in fact, this particular infinity of values is going to get us a particular area of this curve. Or the area under this curve, between the set values. So for this one right here, say that we're going to take limit values going from 0 all the way up to 4. Our function for this was 16 minus x squared, and we had dx for we had dx for the slices that we're taking, infinitesimally small differentials. Now for this, we already learned that doing anti-derivatives is going to be the way to get us the indefinite integral, the one without the limits of integration on top and bottom. For this, with the definite integrals, we're still using the same stuff. We're still using the same antiderivative to get this all set up. So here, the antiderivative of 16 is going to be 16x. The antiderivative of negative x squared, well, we have to think about that a little bit, just for a second, right? We need to have we need to have a 3 out front in order that we might have 3x squared dx become, what is the derivative of x cubed? Right, this is 3x squared. Well, hey, again, almost have it. So now all we have to do is multiply by a, nope. We're just multiplying this term by a 1/3 in order to balance out what we're doing. Multiply a 3 somewhere, we got to multiply it 1/3 somewhere. Okay. And a 3 and the 1/3 had nothing to do with the 16x, so don't touch it. Okay, and then over here, the negative is still going to come down. And when we take the integral of negative x squared, we end up with a 1/3 x to the third. Proper notation, because this is definite integral, is we're going to put the 0 to 4 on the end over here. Well, now what? So, for this, what we're going to do is we're going to say, well, it's pretty obvious that we're going to need to take the ending point of might be easier to see with a different example, but we're going to take the ending point wherever it is, and it's going to be like, we want to, yeah, I need to do the other one first. Okay, so area function, we already did this. It was this. well, it's not f of x, hang on. It's the integral of all this stuff. Is this area function. So now we got to look at this and say, okay, if we want to know area from a equals 0 to b equals 4, ugh. Sorry guys, I'm going to rearrange this. I gotta do better. Right, simple example. Right, find the area under the triangle. Where, or from, a equals 0 to b equals 4, and the function here is going to be g of x is equal to just 1/3 x. Make it nice and easy. Well, we can already calculate this from a being 0 and b being 4. This is a right triangle. It makes it super easy to figure out. If x is 4, then y is going to be 4/3. And so the distance going up the height of this triangle is going to be 4/3. And then for the area of the triangle, we know area is going to be equal to 1/2 base times height. Well, what are all the parts? Our base is just how far we're going in the x direction. Our height is going to be 1/3 of whatever we go in the x direction. So now here we have an area function that is a function of x, which is now going to be 1/6 x squared. Right? Super easy. What if? This is the same triangle. But this time what we're going to do is go from a equals 2 to b equals... I mean, we'll still do 4. That's fine. All right, how do we do this? Well, now we're drawing this halfway mark, and we're saying, we're going to stop here instead. This one's going to be a 2. Its height is going to be 2/3, and its length over there is going to be 2. So how do we find only the area of the
versatile fragrance to be worn day and night, leaving an unforgettable impression. Stronger with You by Imperial Armani. Available now with the perfume.
But instead, right, the same triangular shape, but this time we're truncating it.
Feel like you're talking on Spotify can help your business turn up the volume. With our easy-to-use ads manager, you can create new audio ads.
Yeah, I knew. Once I said it.
Then we'll deliver your ad to an engaged audience who's ready to
Right? So what we're looking for is how do we figure out the area of this thing? Again, we know it's a trapezoid, but supposing you didn't, right? We can't just say, oh, well, this is going to be 4/3 here. We're going to have a 2 on this side and a 2 on this side. And this one happens to be 2/3, but like, I guess we would have figured that out. But anyway, your average calculus student will be able to see that, oh wait, this is just a piece that's taken away from the bigger triangle, which is a triangle itself. Yeah, they call it a trapezium over here. I don't know whether that's the proper terminology, or then trapezoid is like something that is shaped like that, so it also includes rectangles. Because they have at least one side of parallel sides or something like that. I think it is like partitioned. Trapezia or trapezoids are partitioned into the trapezium, which is exactly one pair of parallel sides, and parallelograms, where we have two parallel sides, two sets of parallel sides. So not all trapezoids are parallelograms, but all parallelograms are British trapezoids, but not trapezium. I think. I might have that wrong. I'll ask my kids in the morning. Or I could probably look it up online. It's all good. All right. Ads are going to start here. Let's start a 3-minute ad break. Go get water, stand up, stretch, do all that good stuff, and then we'll be right back.
song tells me we're through. Yeah, but I can't turn it off 'cause it's the truth. And it goes like, yeah, play all I hear is when I press play, all I hear is you. Oh, every single song tells me we're through.
Trapezoid, to me, implies that it is a very vague definition. You know, like... most choose inclusive, yeah. So, you know, I would probably argue that, like when we're talking about paraboloids in three-dimensional algebra, then we don't really care exactly what family it belongs to necessarily, as long as it is parabolic-like, and hence the name, right? Oid, the suffix oid, meaning something like this. It doesn't have to be exactly meeting whatever definitions you have for the thing that comes before it. So in the case of this, right, trapezium. Hey, famished. Trapezium is a specific definition, and trapezoid is going to be something that is like that but doesn't actually meet that definition, or is a vague nebulous sort of thing. So, as far as I'm concerned, yeah, let's go for it. Tonight, hashtag not sponsored by Lotus Biscoff.
And find your nearest vaccination centre at letsgetvaccinated.co.uk.
Alright, so here, with this area, what we're going to do is take the big area, or the area when we go out to 4, and then subtract the area when we go to 2, because we do not want that section over there that's going toward the origin. We only want the section that's out here, which starts at 2 and goes to 4. So in other words, remove the piece that goes from 0 to 2. So for this, we end up with 1/6 4 squared minus 1/6 2 squared. Right, so this is going to be 16/6 minus 4/6. And I'm not even going to bother simplifying these individually, because we can simplify at the end. So 16 minus 4 is going to end up being 12/6. So that's just 2. So this is A of... That doesn't work. That's fine. A of 4 minus A of 2. And so this would be the same thing if we took this and said, oh, okay, let's go with the integral, or the area under the curve, going from 0 to 4 of g of x dx is going to be equal to, in this case, right, 1/6 times 4 squared minus 1/6 times 0 squared. This is all just going to be 0. And then this bit over here is going to be 16/6, or 8/3. And if we do this in terms of 1/2 base times height, just, without combining everything and doing all that stuff, and just doing it with numbers, then we get 1/2 times 4/3, so that's going to be 2/3 times, nope, I did the height first, whatever. 1/2 the base is 4, so half that's 2, times the height is 4/3, so 2 times 4/3 is 8/3, and look at that, we got the same thing in here as well. So then can we translate the same with this one? Can we go from the integral from 2 to 4 of g of x dx? Well, it's going to be the same as here. It's going to be the same as the area function from 4 to 0 subtracted by the area function from 2 to 0. And this also means we have another way of expressing this, because, okay, we could also do this then as the integral from 0 to 4 of g of x dx minus the integral from 0 to 2 of g of x dx. Nope, I don't need that. So all of that is equal to this integral from 2 to 4 of g of x dx. There's more proofs that you can use. This one's easy enough for Calc 1, Calc 2 students, right, who probably don't need a massive formal proof in order to make sure that this works right. We can see that the notation is able to sustain this particular pattern. You're looking into a Blender coffee shop modeling. Oh. Hashtag also not sponsored by a little bit of moonshine. That's the sticky toffee pudding one. So our fundamental theorem of calculus then is going to use the exact same logic to start pulling area functions for all of these higher dimensional higher order polynomials. So for instance, right, the area under 16 minus x squared is going to get us a of x. No, not wrong one. I'm on the wrong part of the screen, and that's just is 16x minus 1/3 x cubed. So for this one, we end up with the same as a of 4 for this particular function. So the area from 0 to 4 is going to get us this. And again, all we really need to do here is plug in 16 times 4 minus 1/3 times 4 cubed minus, parentheses, 16 times 0 minus 1/3 times 0 cubed. So all that 0, we could just get rid of that. That's fine. And then here we have 64 minus 4 cubed is 64 over 3. So 64 thirds. So what is 2/3 of 64? And then we have an answer. So here 64 is not divisible by 3, unfortunately. So it's just going to have to be 128 over 3. So 42 1/3. 2/3. Yeah, 42 2/3. But then, of course, we could just do the exact same thing, but start from A equals 2 and B equals 4, and then end up with the exact same procedure. Okay. Then that means that we want the integral going from 2 to 4 of the original function, 16 minus x squared dx, which is going to then be 16x minus 1/3 x cubed, evaluated from 2 to 4, which is going to be the same as, just like we saw before, a at 4 minus a at 2. What's the area when we go from the origin all the way to 4? And what's the area when we go from 0 to 2? Chop that out. So when we do this, we end up with 16 times 4 minus 1/3 times 4 cubed, and yeah, it's just 2/3 of 64 again, but minus parentheses, the thing we haven't done yet. 16 times 2 minus 1/3 2 cubed. Right, if we want, we can also combine the stuff that's more like each other. So this is going to end up being 32. We know that 16 by 4 is 64, and 16 by 2 is 32. We're trying to subtract those two things. And then here we have a minus 64 over 3. And then a minus negative makes a plus. 1/3 of 2 cubed is 8/3. Right, 32 is going to be 96/3. And then here, 64 is bigger than 8. And then if we subtract 8 from 64, we get 56, which is not divisible by 3. And then when we subtract them, we get 40 over 3. Again, this was a at 4 minus a at 2 for this particular parabolic section, which was the same as the integral from 2 to 4 of 16 minus x squared dx. So what is this fundamental theorem of calculus thing? Well, first of all, we can do this A to B swapping thing, and if we wanted to, this is something that I didn't do. If I wanted to, right, I could have taken the integral of 0 to x, some unknown amount which is going to be based on where we place x. So going from 0 to some unknown x value of the function g at, now here we can't actually use x. We just have to use a dummy variable because we're already using x, and if we put x on the inside, we're going to be in trouble replacing x, the variable, with x the limit of integration. So we're going to choose just some dummy variable. We say like, you know, m dm. And when we take its integral, the antiderivative, we usually just use a capital letter of whatever we're using. And now what's going to happen is that this x is going to become the variable that we're using. So we're using it essentially as a change of variables in order to make that all work. So go use a dummy variable in place of all those x's, which is going to be the variable endpoint. Right? It's totally m, not x. 100%. Sure. Sure. Right, so then all of this stuff is going to be area at x specifically.
It don't matter where we go, it don't matter where we stay tonight, 'cause when I'm with you, yeah, I know everything will be alright. It don't matter what we say, it don't matter how we make things right, 'cause when I'm with you, yeah, I know everything will be alright. When I'm with you, it don't matter where we go, it don't matter if we lose it all, 'cause when I'm with you, yeah, I know everything will be alright. It don't matter if we fall down into the darkest place we know, 'cause when I'm with you, yeah, I know everything will be alright. When I'm with you,
Here I am just talking to myself. I'm a very captivating audience. Right. So once you take the derivative of the integral, this is like undoing the operation that you've done. Now, why is it that x is inside of the x is inside the limit of integration, and then why does it show up again on the other thing? Well, that's because what we're really doing here is we're saying we're taking the derivative of, this is where the second part comes in, the integral of some particular function f of x dx evaluated from a to b is going to be capital F at b minus capital F at a. So if we insert this here, this is going to be capital F at x minus capital F at 0, and then we take the derivative with respect to x of these things, of the f of x and of the f of 0. Well, capital F of x, we take the derivative and it becomes just regular f of x. F at 0, we take the derivative, hey, that's a constant. So it's eliminated. So we just end up getting f at x, and that's it. Okay, but the second part is really important. It comes from all of the area function stuff we were talking about back over here, where we end up saying that in order to find an area of a truncated shape, right, find the area from the origin all the way out to wherever we ended, find the area from the origin to wherever we're supposed to start than the other one, and then subtract that from the bigger, fuller area. So that's our fundamental theorem of calculus. Okay, comes in two parts, like I said. You take the derivative of an integral, and it's going to undo itself, provided that they are on the same function, or sorry, on the same variable, or in this particular case, the p is just a dummy variable, f at p dp. We're going to insert the x as part of the limit of integration. And then when that happens, that term is going to have its derivative taken.
Son of a reflexologist who's currently plant sitting for the stepsister of a social media influencer that lives next door to some guy who works in finance. You just need a little help from Experian to improve your credit score. Download the Experian app and check your credit score and report for free today.
On January 2nd, over 300 people were seriously ill with flu in our local hospitals. That's the equivalent of 10 full wards. So this winter, our best chance of staying well is by getting a quick, simple and free for many people flu vaccination, especially if you're older, pregnant or have a long-term
Okay.
condition.
So one of the problems here,
so get them vaccinated too. Check your eligibility and find your
it says find the area
letsgetvaccinated.co.uk.
of the region that's bounded by the x-axis, the line of x equals 4, and the curve y equals the square root of x. So here, our area at 4 is going to be equal to the integral from 0 to 4 of square root of x dx. Take the integral of square root of x. Well, this is also x to the 1/2. And in order to have a proper form for an antiderivative, we're going to need a 3 halves in front. Right? Because this would be the derivative of x to the 3 halves. Excuse me. But then also, we can't just make the 3 halves appear out of nowhere, so we have to multiply by the reciprocal, 2/3, somewhere else. That is going to stick around. So that 2/3 will stick around. Then we take the antiderivative of 3 halves, x to the 1/2, and we end up with x to the 3 halves. Evaluated from 0 to 4. Okay, which is then going to be equal to 2/3 times, this is going to be 4 raised to the 3 halves, minus 2/3 times 0 raised to the 3 halves. The 0 that's here, nothing's going to change it. It's always going to stay 0. We're just raising it to powers and then multiplying by a constant. So, and then out here, with 4 to the 3 halves, we can go either way with this. You could take the square root, right, the 2 in the denominator, the square root of the 4 first, or you can cube the 4 first. Either of those, I know what they are, right? 4 cubed, we already did up there, was 64. And then we take the square root, becomes 8. Or we take the square root of 4, which becomes 2, and then we cube it, which becomes 8. Times 2 in the numerator is going to become 16 over 3. Okay. And then there is another example of something we did not exactly talk about, but ddx of integral from x to x squared of t over log of t, which again, if you remember, is natural log dt. All right, so in this case, we don't have limits that we can just plug in. We don't have it starting from 0 and going out to a variable amount. In theory, we could also have could also try and get some involvement with integrals that go from 0 to x and then 0 to x squared, so that we have all 3 of these represented. I don't think we're going to bother with any of that. Okay, so what we should do instead is look at this and say, let's just pretend for a minute that this is just the integral of this stuff. I don't know what that is. I'm pretty sure it's going to be a nasty integral, and it's not actually going to come up with anything useful. It may, in fact, be impossible. However, let's assume that f of x equals t over ln of t. And this has an antiderivative. Capital F of x. Oh, sorry, f of t. Therefore, the antiderivative as we go from x to x squared of t over natural log of t dt is going to be equal to f at x evaluated, hang on, f at t evaluated from x to x squared. Which is going to be capital F at x squared minus capital F at x. Okay. Now let's look at it in context because we also have a derivative. So the derivative of the integral from x to x squared of t over natural log of t dt is going to be equal to the derivative with respect to x of f of x squared minus f of x. Right, ddx of capital F is just going to be lowercase f. And it's of x squared times, here's where we have to go in and say, well, by the chain rule, this would also go in and take the derivative and say that this was going to be 2x here. Okay, minus, same here, it's just f at x. Derivative of x itself is just 1, so we don't need to do anything else with that. So we've got 2x times the f of x squared minus f of x. And this is our derivative of the integral that's how we deal with it. Not to say it's easy or anything, but you know. Okay, and that's equal to 2x times, what is f of x squared? Well, we had, right, f is going to be t over natural log of t, or right, x over natural log x, so x squared over natural log x squared. If we want, we can drop the 2 out of the x squared in the denominator. And that's going to end up being 2x times x squared over 2 natural log x, and the 2's can go away. So we get here x times x squared is going to be x cubed over natural log of x.
You've read our prospectus, browsed our website, and seen our ads. Now it's time to visit Harrogate College in real life. Our open events are the perfect way to explore all we have to offer, meet our industry experienced teachers and talk to them about our career-focused courses, tour
Oops.
our first-class facilities,
Minus f at
and
x.
see where you could be learning the skills needed to realise your dreams. Plus, our friendly admissions team are on hand to help. You can even make your application before you head home. Ready to realise your dreams? Search Harrogate College Open Events today.
Making an ad for Spotify is easy. You just write a script, pick background music, then let us create your ad for free in as little as 48 hours. Learn how Spotify can add more to your mix.
Right, x cubed minus x all over natural log of x. Alrighty. Any questions? I'm gonna have to change the stream title again. Man. Okay. Let's go over and see Penn Center, who's doing story time with the Color Cone and Academy of Useless Ideas. So, we will be back on Sunday to play the long game, and then we're going to be back after that on Sunday with Satisfactory. So, hope to see you all soon, and thanks for coming. I'll see you all in a bit, and I hope you're going to have a wonderful rest of your week. Stay mathy or something like that, and I'll catch you all later. My name's Obi-Wan Pez. This is N Simplex Pachinko. Till next time.